shalt build thyself an ark measuring 300 cubits in length.
300 cubits, give or take.
Exactly 300. And thou shalt takest 2 of every creature.
2 creatures?
2 of every creature.
Even stink beetles?
Especially stink beetles.
Whoa, cool. God is so in your face.
Yeah, he's my favorite fictional character.
It's so late. You kids have to go to bed. But the flood's only knee-high. At least let us watch the midgets drown.
Yeah, Mom, come on. You let us stay up to watch Troy McClure and such other Bible epics as David versus Super Goliath and Suddenly Last Supper.
Go, Lise. Way to cite precedent.
All right. You can stay up late tonight, but tomorrow, everyone's going to bed at 5 o'clock.
Woohoo! Go forth, Noah, and remember, the key to salvation is...
You've seen the movie, now meet a real-life Noah. Only this Noah has been accused of killing 2 of every animal. Coming up next on AM Springfield.
Oh, my goodness. That was a long
Lighten up, Lise.
Finland, let's see that native dance.
Where's that Elvis? And I'm doing smart. Sit down. Poland, tell us about your name,
Well, I heard they sent a rocket to the sun once at night, and there was that submarine with a screen doors.
No. Young man, you need to do some serious boning.
Oh, grow up, Lise.
Okay, Libya, exports.
Yes, sir, you American pig.
Nice touch.
Let's see. The exports of Libya are numerous in amount. One thing they export is corn. Or as the Indians call it, maize. Another famous Indian was Crazy Horse. In conclusion, Libya is a land of contrasts. Thank you.
Ow! I can't breathe. Please stop him.
No, I'd like to, but I'm afraid he has diplomatic immunity.
Point of order. If we want to learn anything, we must respect...
Point of order, Lisa stinks.
Hey! Leave her alone.
You leave her alone.
Order! Do you kids want to be like the real UN? Or do you just want to squabble and waste time?
Have a great weekend, kids. Be nice to the underprivileged countries.
Good luck, Ralphie. If your nose starts bleeding, it means you're picking it too much. Or not enough.
Okay, kids, Otto's in charge. Remember, Otto, we're trusting you with our greatest natural resource, the school bus.
Water bill, third notice. Jury duty, third notice. Mortgage bill, second notice. Flancrest Enterprises.
Oops, that's for me. Flancrest Enterprises is my home business.
You liar. You don't have a home business. Why would you make up a lie like that?
No, it's true. Ma and I sell religious hook rugs over the internet.
Internet, eh?
Yes, indeedy. Making some good scratch, too.
Scratch, eh?
Yep.
Maud, eh?
Homer, what are you doing?
No time to answer that, Marge. I'm setting up a home office for my new business enterprise.
What business enterprise?
Ever heard of a little thing called the Internet?
Internet, eh?
Oh, yeah. Everybody's making money off the Internet except us. We've fallen behind. Way behind.
Is that my good butter?
Can't discuss that now, Marge. I have to write another delicious memo. Memo.
63 bottles of beer on the wall. 63 bottles of beer.
Oh, this song is driving me crazy.
B-I-N-G-O, and Bingo was his name, oh.
Man, I don't know why I bought this stupid tape.
All right, and that is the connection to CS50. All right, welcome back to CS50. This is the end of week 2. So a couple of announcements. If you did the hacker edition of PSET 0 and still have a sensor board, that's fine. Make sure your name, username, and ID number are on a piece of paper in the Ziploc bag and just hand it to one of the teaching fellows on your way out today. We've gotten plenty of responses regarding lunch with me and the CAs and TFs. We will follow up by email sometime tomorrow to figure out the logistics. And it turns out, if you're nice enough to one of the houses on campus, they invite you to dinner. So we now have a dinner with David and team next Wednesday. It's part of their senior common room event. That space for that is very limited. The idea is to get together around dinner time in the Mather SCR as well as in the dining hall and to chat and get to know some of the TFs and CAs and fellow students in the class as well as some fellow Matherites. So if that is of interest, next Wednesday as a one-time thing, cs50.net/dinner to RSVP. Speaking of David, there's no need certainly for formalities in this course. It is perfectly fine to call me David. And in fact, sweet as you are at the end of these lectures to do things like this, it's really just a computer science lecture. So there's no need for that either. But thank you. Sections have happened. Sectioning has happened thanks to Jansu and Yuki last night, who used their computer science skills to take a very large data set from FAS and also from our own database, mash them together in email, 300 plus emails out automatically. If you ended up by algorithmic chance in a section you're not going to be comfortable in, whether because it's too much or too little comfort, that's fine. Just go ahead and email section@cs50.net no later than this Friday. Or if you simply can't make your assigned section time, email us as well. Office hours have continued to be in progress, especially now as Friday's deadline's coming up for PSET 1. If you're having any discomfort or you're kind of freaking out because you just really don't know how to do C or program, it's totally fine. Realize there will be plenty of one-on-one help in the Science Center. You can take a look at cs50.net/office hours for the current Google Calendar. And this is an opportunity to, as you can see, it all barely fits because there's so many people who'll be there in attendance. But let me at least ask this. Marta, this past Sunday, did deliver the first walkthrough for PSET 1. You can find the video for that or the MP3 on the problem sets page on the course's website. So if you're asking yourself this question, I have no idea where to begin, how do I do so? Do at least start with that video as it's meant to answer precisely that question. And I realize that we go quickly in the course and that I've put up, a dozen or more programs in C already, and a lot of it might very well feel like this. But honestly, if you've not yet sat down to do problem set 1 and plan to tonight or tomorrow, I think you'll find once you spend some time with this stuff getting your hands dirty, it will all begin to sink in and not feel so cryptic. Finally, turns out it's a big mistake to off the cuff say something in lecture like, gee, maybe you should all check the map to make sure you submitted problem set 0, because this induced innumerable personal emails to me. And I then had to go through our survey data checking whether or not everyone in fact submitted or if it was a Google problem. Version 1 of our little map had a couple of bugs, one of which was Google induced because we tried to hammer their servers a little too fast. They don't like it when we send 350 plus requests within like 5 seconds for GPS coordinates. So they essentially blacklisted us once in a while. That meant some of you didn't make the map and so forth. So anyhow, sat down last night, redid the whole thing, and what we now have is a full-fledged little application here. Much prettier, I think, than the original version, because I also addressed some other issues. I also realized, perfect though this version initially was last night around 1 a.m., unlike my 8-core, 3 gigahertz Mac Pro, I then pulled out my laptop, which is far slower, and the thing sucked. Like, it took multiple seconds just for the page to load. We had this map on our home page. Didn't feel like the best idea for people's first experience to the site to be a little spinning globe or whatnot as the thing loads up. So we rewrote the whole thing, and what you now see are little hotspots, because one of the reasons for the speed degradation was that when you try to put 350 of these little cartoon markers on a map, that takes a lot of CPU cycles. It's a lot of JavaScript code to make that happen. But now it's a little fancier. So now you can zoom in, and then as soon as you are closer to the Earth, it then shows you with more granularity where things are. I can keep zooming and zooming in here, and we can finally get into the downtown Boston area. And in fact, John and David J. are, in fact, from Boston, Massachusetts. So this, too, was an interesting bug. At first, I didn't realize that if you try to plant multiple markers, i.e. multiple students or staff, at the exact same GPS coordinates, Google pretty much just shows the last person you put there. So this felt a little sad because David J. was the last one put there. And I realized, damn, I'm about to get an email from John, quote unquote, if I leave him off the map. So we fixed that, too. We figured out what kind of algorithm it would take, though only a few lines of code, to make a comma-separated English list of names like John and David J, putting the commas in and the and. So there was actually a lot of little bite-sized programming projects that arose as a result. But do feel free to play. And I think you'll find that CS50 students do hail from all over the world. And what you can also do now, if you don't see yourself, or if you're smack dab in the middle of the ocean where there's in fact no land because of a typo, click on Login at the top of the page. You can then click About Me, and you can now change your own hometown. No need for all of the emails anymore. So we've hopefully empowered you for that. Any questions, logistical or otherwise? I'll admit, it's actually really kind of neat to just point and click around and just see from how all over students in this class actually are. So have fun with that, if you will. All right. So I thought we'd take a look at a little bite-sized program that I actually whipped up right before class to address a question or challenge that a number of you have run into, and that's this problem of imprecision. So you've been looking at problem set 1, or starting tonight or tomorrow, we'll be looking at some matters of imprecision. And remember that that just boils down to this problem of C and a lot of languages only using a finite number of bits to represent some value, some number. So if you've only got a finite number of bits, clearly there's an upper bound on just how precise you can be, how many numbers after the decimal point you can express. And a really simple way of seeing this, as a footnote in problem set 1 says, is to try to represent in a float the very simple value of 1/100th. So 0.01. Such a small number. Feels like it should be represented perfectly cleanly underneath the hood, because my God, it's such a common, a simple, relatively small number. But what you see here is that's not in fact the case. So I wrote this really quick program. A float f is initialized to 0.01. And realize that some of these things are just conventions. That's equivalent to leaving off the leading 0. This is not equivalent, obviously, mathematically. But I really wanted to see this value. So instead of just printing the value with %f, I used 0.10f, which even though feels like I've just transposed 0, 1, it actually means something different. What does it mean if I say %.10f? Yeah, so 10 decimal places. So the point just means after the decimal point in this program, show me 10 decimal places. So what that means is I'll actually be able to see exactly how, or more exactly how, this program is represented underneath the hood. So let me go ahead and run GCC on imprecision.c. I'm now going to run the default name of a.out. And what I see is, aha. So even though I, the programmer, have been completely clear about what number I want to express, C just can't quite give it to me because of the judgments it has to make as to exactly which numbers it can represent precisely and which it's going to have to represent almost. And you can see it here. But had I done this, had I just printed it out as a %f, notice that that kind of detail is kind of lost. So this actually looks much better, right? By default, if you don't specify the point something f, you just get some number of decimal places. It looks like the number's in fact correct. But as some of you have realized intentionally per the problem set, you start to trip over some subtle bugs. If you're trying to make change, especially in problem set 1, you might realize that occasionally you're giving the wrong number of coins back because the rounding is off. So that begs the question, and some of you have already had or solved this question already, well, how do you round? Well, if you can imagine the name of a function existing, it might very well exist in fact. So there is in fact a function called round. So what I wanted to demonstrate here was the following. I just want an int. I'll call it the generic I. And I want to initialize I to the result of mathematically rounding the process of moving f's decimal point 2 places to the right. And this is very similar in spirit, of course, to what you're doing in the problem set. So if I have 0.01, I want to move the decimal point 2 positions to the right. And hopefully the answer I'm going to get back is, in fact, 1. But let's see what happens if I do this the simple way. So let me actually undo the fix that I ultimately put in place. So I'm going to get rid of this rounding altogether. And I'm just going to leave it as this. So I gets f times 100. That's so simple. It should just move the decimal point. I know I'm going to lose the rest of the decimal points because when I change from a float to an int, remember, you cast away all the stuff after the decimal point. Now notice I'm using %d, so that's in fact correct. So let me go ahead and recompile this, rerun it. And you know what? If I take 0.01 and move the decimal point on paper 2 places, I'm pretty sure I don't get 0. I get 1. But that's because, notice, if we move the decimal point in reality, the value I'm getting is really 0.999999998. So if you then change that value to an int by throwing away everything after the decimal point, obviously you lose all of those numbers, and all you have left was the thing to the left of the decimal point, which was in fact a 0. So let's go ahead and fix this. Well, it turns out there is a function called round. I express it simply by doing this. It's in a header. It's declared in a header file, not surprisingly perhaps, called math.h. We haven't used it before, but that does in fact exist. It doesn't matter usually what order I include these files in. I just tend to be a little anal and do things alphabetically so I can find things more quickly when I start to get more of these things. But it's in math.h, so it looks like I have a solution. So gcc imprecision.c, enter. Damn, so close. But even though you might not have written this code yet, what is clearly the problem? Yeah, so I haven't linked in, so to speak, the library. So even though standard I/O, as the name suggests, is just so standard that you don't have to say something like -l stdio, because C links in the standard library automatically. But the math, even though it's pretty common, it's not standard, so to speak. So I actually have to tell GCC not only where to find the header file, math.h, but I also need to tell it to link in the math library. So I'm going to go with my gut. I'm going to say -l math. And realize there is, in fact, no space after this, weird though it looks, and hit enter. Cannot find -l math. All right, so some of you have solved this already, but remember the RTFM proverb from last week. Let's just check the man page. So man round. So hopefully there's a manual. And in fact, yeah. So this is the round function. It's apparently in chapter 3 of the manual. And notice, OK, I got this part right just by guessing. I see that there's a few versions of round. The one I used is called round. You pass in a double or a float, which is not even as good. Here's the hint. So again, the manual answered this question. So let me go ahead and fix this. So gcc not -l math -lm. OK, that's pretty good. Let me rerun the program. A.out, and now I have the answer. So we'll see another trick later today for how you can implement round without even knowing about this round function. But the exercise here is that if you think that there might be a function, a utility function of sorts, we'll check the man page for the name you might think it has. And more than that, especially if you've not gotten ahead and gotten any of the recommended books, which really aren't necessary, you can go to the resources page of the course website. Under C, by far one of the best references here is this thing. C reference. We took this from cppreference.com, C++ reference, ripped out all the C++ stuff, and left just the C stuff. And you know what? I want some math functions. All right, standard C math. OK, interesting. It looks like C gives me all of these things, most of which I don't need. Oh, there's a POW function. You might find that useful at some point, but not necessarily required anytime soon. But I wanted, interesting, that round is not documented here. Let's see, display all entries. OK, well, we won't waste time on this, but somewhere in here is it actually embedded. For some reason, not here. Do I want to? Damn. All right, that's an interesting omission. So for every other function except round, turn to that documentation, which I promise you is outstanding. But it actually is a good way of just learning some new tricks, right? We can only cover so much in lectures and even in sections. And frankly, you'd get bored quickly, I think, if we spent an hour saying, here are the 15 functions provided by the math library, and here's 15 examples of each. I mean, that kind of stuff you can just kind of flip through when you care or when you need to. And again, that's all about how one bootstraps him or herself into learning a bit more about a given language. So let's go ahead and learn a bit more. So We started last time with a bug. Let's start this time with another bug of sorts related to this very simple idea of swapping two variables. Out of context, really not that sexy to say, I want to take this variable and move its value into this and this value into this. But it's actually a relatively simple exercise that triggers some problems. So in buggy3.c, which is in your printout from Monday, or if you weren't here, there are extra printouts probably still outside. I decided this week today to take off the training wheel, so to speak. So even though I've been very good in putting comments, as you should in problem sets, in the printouts of this code, I wrote a little script that rips out all of the comments from the code I'll display on the screen, only because I realized that if I continue asking questions like, what does this block of code do? And the answer is there, expressed in a comment, really not all that stimulating. So realize you have the answers in your handouts if you need to glance or reference later. But for the sake of engaging, try to focus up here when interesting topics come up. So here is a function. It's called main. That's my default function. This is kind of interesting. There's something interesting and new going on up here, but more on that in a moment. So what does main do? Main declares two variables, x and y. It gives one the value of 1, one the value of 2. This program is going to print out each's value. Not very interesting. Then it's going to say swapping ... And then it does what? Well, in English, what is this line of code doing? Like, how would you express, now that you're getting a little more comfortable with programming in C, what is that line doing in English? Yeah, so I'm calling a function. The function's called swap. And presumably, it's meant to swap x and y. Because if you kind of think ahead where this program's probably going, I'm probably trying to demonstrate that x and y are 1 and 2. But then I call swap. And now they're 2 and 1. All right, so let's see if that is in fact the case. Let me go ahead. This is buggy3, so make buggy3, enter. And now notice, incidentally, one of the upsides of using make, even at this point, instead of running GCC manually, which is also instructive, realize that all the stuff it spits out automatically has, among other things, linker flags like this. So we sort of aggressively provide you with flags like -lm, just because we figure if you're running make, you don't want to have to think about details like that. But realize, if you've been using make, some of the magic has been happening because of our automation of that here. So now I have a program called buggy3. It's in my current directory, so I'm going to start getting pedantic with // to say this directory, program called buggy3, enter. Apparently, it doesn't work. So it's broken. It's buggy. So why is that? So let's take a quick look. This code looks pretty good, right? It's hard to find. Maybe you have found, but it's hard to find any fault logically with the code in main. So maybe, presumably, it's in this swap function. Maybe it just doesn't do anything. So let's look. If I scroll down, OK, all right, somewhat of a new approach. But here, too, realize even though I'm calling some of these variables a, b, and temp, which would seem to violate this principle of good style, well, realize that there are some contexts, like iterating in a loop. We're just calling the variable I, though simple, is very reasonable. Calling a number, a counter n, very reasonable. Calling a 4-line functions variables a and b, because that's really all they have to. The function doesn't have to do all that much. Realize that sometimes completely legit to use very simply named variables. So in this case, how do I swap a and b? Well, if I've got a here and b here, I can't just copy a to b, because what happens if I just do b equals a semicolon? All right, I lose b, right? I'm kind of doing too much at once. So what would you do in reality? Well, you can't just move this here and then this here because of that problem. So let me just move b into a temporary variable, a little placeholder. Then I can clobber his value, change his value by doing a gets b. And then finally, I can restore b by using, per this last line here, that temp variable. So there's a trade-off here. Subtle though it is, the trade-offs will become more interesting over time. But notice that I'm using 32 extra bits to implement this particular function. I'm taking a and b, I'm swapping them. But to make that happen, I actually need, in this implementation, a bit more memory, but not such a big deal. But apparently, it's still wrong. So why? Can you find logical faults with this? Or even if you're maybe among those more comfortable, you can express what the problem is. Why is swap not apparently swapping? Yeah. So I'm not returning anything. So that's an interesting point. So swap is declared as having a return value of void. So that's interesting because it's certainly not printing anything. And the last time we saw a function that didn't print anything, it really didn't do anything useful. It didn't even have any side effects. So that could be the explanation here. So it's not returning something. And certainly up here, notice I'm not even assigning a variable the return value of swap because its return value is nothing. It's void. So I could fix this that way somehow. But what else might the problem be? Yeah? OK, so that's an interesting gotcha, too. I seem to be talking about x and y up at the top here in main. But then all of a sudden, I start talking about a and b. So clearly, x and y aren't getting swapped because I'm only swapping a and b. So there's a couple of interesting takeaways here. So that's true in this case. And that's it's not fundamentally the explanation, but it's definitely related. So in this case, yes, I have two variables in this context of main called x and y. I go ahead and pass them in as what we'll start calling consistently arguments. So arguments are inputs to functions, otherwise known as parameters. Slight difference in terminology depending on the context, but for the most part, they're synonyms. So a function can take arguments or inputs, and that obviously influences behavior. Think back a week, printf takes an argument. It takes a string and maybe multiple arguments separated by commas, the variables that then get inserted into that string. So we've seen this before. So inputs to functions are called arguments or parameters. Well, it turns out the way these work is as follows. If I have a variable x here and a variable y here, notice that in the function that I'm calling, I need to give those inputs names. Now, I could coincidentally name them x and y, but that's not strictly the case. Right? Consider, after all, that you guys have no idea what the person who wrote printf called those variables. You've been passing in quote unquote and then a string inside of it and maybe comma x, comma y, comma z. But hopefully that programmer who wrote that function 20 plus years ago doesn't have to know or care what your variables are called. He or she can use his or her own variable names. And so that's in fact the case here. It is completely my prerogative to call these things a and b, foo and bar, anything I want, because what happens when you call a function and pass in inputs usually, a copy is made of the inputs. So yes, I have 32 bits up here called x and 32 bits up here called y. They're storing a value, 1 and 2. What happens when I call swap is that a copy of x and a copy of y are passed in. And now in this scope, so to speak, in this context, I now have copies of x and y. They're called a and b. There are different 32 bits for a, a different 32 bits for y. Are these four lines swapping, do you think logically, a and b? Like, is the code at least correct? So yes, right? There's no logical fault with doing this. I have a temporary variable. I keep a around. I clobber a with b's value. Then I update b's value with a's former value, which I tucked away in temp. So logically, if you think this through or even kind of play around with a simulation on a piece of paper, that's correct. But at this point in the story, at the very last line of this program, what is a's value? So what is a's value where the arrow is there? So 2. And what is b's value? 1. But what are x and y's values? They're still the opposite. They're still the original values because, again, these are copies. So the key takeaway here is that when you actually call a function, you get a copy of the variables that are being passed in. Now, we'll see in time that there's a solution to this. But the fundamental problem here is that functions like swap have their own scope, so to speak, their own context, their own dedicated memory. So yes, you can pass inputs to a function like swap. And yes, that function can manipulate those numbers, do some math on them, even print out things a la side effects. But it does not have the capability to change the original variable's values, at least not yet. So we can see this in one other context here. So let's take a look at just this little snippet. So here's a function called increment. As the name implies, its purpose in life is just to increment a value called x. Well, I claim that this is identical in spirit to this same problem. Let me go ahead and open buggy4.c. Scroll down. Notice that I'm even claiming a simpler program here. X gets 1. Quote unquote, x is now 1, presumably, incrementing, ... I call increment, and now I claim it's incremented, and then, OK, x is now 2, hopefully. So let's do this. Make buggy4, enter. Increment, that's interesting. Error. Oh, OK, that was the bug. OK, not an error. That's intentional. So notice what happened. I'm going to do it more simply with GCC. So GCC of buggy4.c. OK, in function increment error, x is undeclared. But wait a minute, I'm pretty sure I had int x. So what does this mean? Well, if you haven't realized it already, if you get errors from GCC, they're cryptic a bit, but they also have some juicy information. The name of the file that's got the problem, colon, the line number that GCC at least thinks the problem is on or began on, and then hopefully an instructive error message, as is in this case. And realize, too, especially if your first experience in the Science Center on your laptop with CS50's pset is to get not 3 lines of errors, but like this many lines of errors, realize that early on can a stupid or simple little problem just trigger a whole lot of confusion. So again, if your first reaction to your problem set is, oh my god, I wrote 10 lines of code and generated 100 lines of errors, fix the top ones first, because there's often a cascading effect, right? So don't pluck off the one you understand because it's in the middle. Start from the top down, and you'll likely knock off multiple bugs at once. So let's look at line 40. So notice I'm using well, let me use nano here for a second. So buggy4.c. Notice if I scroll down, notice that the line number is changing. So I can see, aha, line 40 of 42. So it's not a very long file, x++. So here, too, we see the fundamental problem of scope. Notice in the top of this program, buggy4, I declared x, int x. That was good. And then I assigned it a value of 1. But now in increment, the increment is a function. Increment has its own scope, its own context, its own chunk of memory to play with. And guess what? X was declared in someone else's scope, namely main. So you can't just start talking about x in the context of increment, because who knows where increment is being stored in memory. Increment knows nothing about main other than what it's told. And apparently, I have told increment nothing because I didn't pass in any arguments. So this program fundamentally doesn't work because I'm trying to increment a variable that just doesn't exist in that scope. So what's a solution, perhaps, to this problem? How can I at least get this program to compile? What could I do? So I could declare x. So I could say something like, all right, well, if the problem is that I didn't declare x, to declare a variable means to give it name and give it a type. Well, let's say this, int x. All right, does that fix it? So no, obviously not. That does give me x, but a problem in C, as in many languages, is if you don't initialize a variable, who knows what's inside of it, right? People have been using this computer before you. You on your own computer have been checking email, checking websites. So a lot of your RAM's been in use. And who knows what zeros and ones have littered your RAM at this point in the story. So when you just say int x, you're just telling GCC, give me 32 bits of space. But if you don't tell GCC what to put there, the computer is pretty much going to hand you whatever was already there. Now, that's a bit of a white lie because some operating systems do scrub the memory. So what you would actually get back in some programs is all zeros, which is better than just complete nonsense. But the rule of thumb for today and for a while, realize is do not ever fail to initialize your variables. Do not assume that they will be 0, because weird, bad things will happen. So this does work in terms of compilation. Right, let me go ahead and save this. Save modified buffer. Yes, enter. Let me go ahead and rerun GCC. That made GCC happy. But it didn't make the logic of my program happy, because now I'm incrementing, let's see, now a.out. Now I'm incrementing some other variable that, yes, is 32 bits, but it's a different 32 bits. And so, again, I haven't really solved the problem. So what then is another solution to this problem? Like, how could I go about fixing this problem in buggy4.c correctly, quote unquote? Yeah. Yeah, so what if the problem is, so the short answer is, what about using a global variable? Not something we've really touched on yet, but it's a simple idea. If the fundamental problem is that x does not exist in the scope of increment, it only exists in the scope of main, well, is there some other context, some other scope that all functions can see? I feel like intuitively I could get away with some trick like this. You know what? Let me say x gets 1 there, but you know what? Let me just try declaring x outside of every function. Because if you think of it now as x being viewable by the entire file, this kind of makes sense. Now x is in scope for everyone because it wasn't declared inside of any particular function. So let's see if this works. Let me save this. Let me run GCC on buggy4.c. OK, compiled. So that seems to have been progress. Now let me go ahead and run a.out. Voila. So that did, in fact, fix the problem. So yes, global variables are a possible solution to this problem. But now what we just handed you as a solution, we kind of need to take back. So in general, using global variables, bad. OK, that's sort of the mantra within programming, because global variables very quickly become a mess. It becomes unclear when you start writing programs that are not this long, but this long and spread across multiple files. It's not clear where they were defined. Realize that as things get more sophisticated, we'll introduce better ways of solving this problem of scope. But in this context, for such a simple problem of incrementing a counter, which frankly seems to have little real-world value just as of yet, this is an adequate solution to this problem. So for now, it's a tool in one's toolkit. You have this ability to use global variables. But clearly, per the previous examples, do we have the ability to pass in inputs and get outputs? So in general, you should take the latter approach. So I promised to explain what this is here. So this was buggy. Actually, let's go back to buggy 4 since we're already on it. So this is buggy 4. And notice that it, too, at the very top of the page, has this, which looks like a function, but it's missing what? Minimally. There's none of those curly braces. Every time we've declared a function thus far, we have open brace and then some code, right? It's missing code. But there seems to be this coincidence. A void increment, open paren, close paren, semicolon. That looks awfully like this thing here, except I got rid of the code, I got rid of the curly braces, and I slapped on a semicolon, and also got rid of the line break between void. Incidentally, you'll see different conventions. This is a matter of style. A lot of books, a lot of people will write code like this on one line. Personally, I actually tend to put the return type on one line and the name of the function on the other, because with sophisticated text editors, word processors, you can actually search your code and say, you know what, I know I want the function called increment, but I want to find it when it's the leftmost character on the screen, because then I can find where I implemented it, not where I called it. So there's little tricks like this you pick up over time. But it's just a matter of style. So why do I have this seemingly redundant mention of increment up here? Well, my program is working, right? We fixed it with the global variable. Let me go ahead and delete this for now, the seemingly superfluous line. Let me go ahead and run gcc of buggy4.c enter. All right, let me redo that. Maybe it's not my fault. Maybe the computer screwed up. OK, probably not the computer's fault. I'm doing something wrong. So what is it? Well, fortunately, again, GCC is being a little helpful, but it looks like I made 3 mistakes. Line 23, line 38, and OK, line 23 again, so that's 2 mistakes. But what's the warning saying? Implicit declaration of function increment. So the short explanation of this is that C is just kind of stupid. It's an old language, so it's a very powerful language. But when efficiency was more important than user-friendliness, certain decisions were made. For instance, the decision was made that you cannot call a function unless you've already declared it earlier in the file than you're actually calling it. So what does that mean? It means if I want to, in this line here, call the function called increment, well, it had better have been defined somewhere previously in that actual file. All right, so there's clearly a fix for this. So this is, let's see, let me just go ahead and cut these lines using a little text editor tricks. But you can just copy, paste, and nano in different ways, or just retype. Let me go ahead and paste it here. All right, so if the problem is that increment was defined, was implemented after main, well, an easy fix is just define it before main. So let me go ahead and recompile. Let me go ahead and run GCC, and that seems to have fixed it. A.out, enter, seems to have worked. So does this mean the simple solution is just always put your functions above main? So maybe, but there's some pushbacks here. So one, when you open a file, the program ultimately runs main first. I, as the reader, would just really prefer to see what the program does first. I don't want to see increment. I don't want to see other random functions. I want to see the main function first. So just in terms of friendliness and readability, feels like it's a good practice to put main first. But then you clearly run into these problems. And if you really think this through, you'll run into scenarios where if one function calls another and then he might call that guy again, right, you run into a problem where, OK, this guy has to go here, but this guy has to go here. Like, you'll run into this endless loop where you're in this catch-22. Everyone can't go in front of everyone else. So there is a solution to this problem. Not only can you define a function To define a function is the very precise terminology for implementing the function with actual code. You can also declare the function by simply stating at the very top of the file what the return type is, what the name of the function is, what its arguments, if any, are, semicolon. So at the top of most any program you write that has multiple functions within, you just have to get into the habit of declaring your functions at the top of the file, right? It's kind of a nuisance. Java does not have this downside. PHP does not have this downside. It's sort of an artifact of the fact that when this language was really first in use, it took time for the compiler to read the whole file from top to bottom, left to right. So it's not going to waste cycles and waste human time by reading it once just to figure out what functions you wrote and then go back with that knowledge and start compiling. So it was that simple reason there. So it's minorly annoying these days, but very simply solved. Well, let's look at one last buggy example. So here we have a very similar variant to what I initially tried to do. This program compiles, and this program has a global variable. Look at the top of the file, int x. Here's my function declaration. Here's main. Here I initialize x to 1. What do I do down here? Do you see already why this program is not, in fact, going to increment and then print the value of 2? What's that? So I didn't declare it as an int in main, but that's OK, because is there an x in scope at that point in the story where my cursor currently is? There is, because I declared a global variable called x up here. So this variable is in scope everywhere, which means it's certainly in scope here, which means at this point in the story, I am successfully initializing x to 1. But notice what happens if I run this thing. So this is buggy5, GCC of buggy5.c. Let me go ahead and run a.out here, a.out. Apparently, the code is broken. It did compile, but the code is printing 1 both times. What is happening, do you think, given these concepts of today? Yeah. Yes, I declared x twice. And because I declared x twice in a more recent context, one that's actually enclosed in these curly braces, this declaration of x in the bottom of my file is, quote unquote, overshadowing or shadowing the original declaration of x. So this is completely fine. You are welcome as a programmer to use the same variable name in multiple contexts. But if you pick the same name that's all still in context, still in scope from elsewhere, you're going to shadow it and end up incrementing x, yes, but what is the value of x at this line in the file? 11, but it's this copy of x, this 32 bits that was declared inside of increment, not the 32 bits that was declared at the very top of this file by way of a global variable. So again, another subtlety, and this one is actually a good thing because it means that C keeps things very tight. If you declare a variable in a function, that's the one that you actually have access to. But there's actually an interesting explanation for all of this. And this is just a teaser because we'll start to peel back these layers in future weeks as to what's really going on. But for today's purposes, long story short, your computer and nice.fas.harvard.edu, it has a bunch of RAM, probably like a gig of RAM, 2 gigs, 4 gigs, whatever it is these days. And if you think of your RAM, I mean, physically, they're these little silicon boards, these little chips. So if you think of them literally as a rectangle, and inside of that rectangle are a whole bunch of bytes, billions of bytes if you have gigabytes of RAM. Well, what happens when a program runs is its main function first takes some of the bytes from the very bottom of your bank of RAM, so visualized here. So main's parameters, any inputs to main, which we'll start using today, end up at the bottom of your RAM. If you think, again, of your RAM, your memory, it's just some big rectangle. So when main is actually called, main can have local variables. Variables like x, variables like those we've seen in examples, those get put next into your RAM, so from the bottom on up. Meanwhile, if main happens to call a function called foo, well, if foo takes some arguments, if foo takes some parameters like a and b, those parameters are stored next in your computer's RAM. So above, conceptually, main's memory. Meanwhile, if foo itself has some local variables, temp, TMP, that 32-bit integer, those, meanwhile, get put next into your computer's memory. So what the point of this story is that when we talk about scope or we talk about context, what we're really talking about are, conceptually, these different chunks of RAM that are being allocated from your program start to finish as it's actually running. And the fact that foo has its own layer there, its own frame, as we'll start calling it, that's distinct from main, that means that main does not have access to foo's chunk of memory, because just look at it. It's in a different place in the computer's memory. And things called global variables are actually stored somewhere else altogether. This is a more complete picture of the story we're beginning to tell and will continue to tell over time. Global variables are actually stored way at the top of your computer's memory, along with what's called the text segment. So all those zeros and ones that GCC outputs, when you run a program, they've got to be loaded into RAM off of your hard drive. They, too, end up at the top of the rectangle that is your chunk of memory. Any questions? OK, that was a lot. Let's take our 5-minute break a bit early today. All right, so we are back. So let's solve this problem in one way, just to equip you for one possible approach. And it was actually proposed already here in the crowd, was to use a return value. So again, the problem was that we're running into problems of scope. It somehow relates to memory management, which is a topic we'll revisit. Well, one approach to this problem of scope would be, yes, don't just have a local variable whose value gets incremented and then do nothing with the result. Return the result of your hard work. Return the result of those mathematics. But for this to work in the context of incrementation, we're going to have to make a change. If I want to increment x, maybe I should actually provide x as an input to the function so that that function has access to it. And you know what? Don't just let that function increment x, or a, if that's what the name is that it wants to give it. Go ahead and actually have that function return the result of its mathematics. But then the burden is back on me, main, to actually keep it around. So a relatively simple logical fix to that particular problem. But let's see how else this can be expressed. So this now is maybe slightly more compelling, right? We already have a way of incrementing values, something plus plus. So that's not that interesting. But you already have been inclined, some of you, to turn to the math library for rounding. So there's certainly little bite-sized problems that would be really nice to factor out and put inside their own method, or inside their own function. And maybe another such example, similar in spirit to round, is a cube function. If you want to take a number and raise it to the power of 3, yes, you could do x times x times x all over the place, but it feels a little cleaner, or should start to feel a little cleaner, to actually outsource that to a dedicated function, like a function called cube, define it as taking one argument called x. The name I give this argument does not matter. And because this is such a short function, I'm really not going to give it an interesting name. It's really not justified. So return a times a times a. So again, just a slightly more useful function here. It does, in fact, solve the problem, because now at the top, I pass in x as an argument. It does the math and returns the result. And then I keep x around as a return value therefrom. All right. So enough on scope for a moment. Let's actually segue to a topic that ultimately will be related, because it boils down to manipulation of memory. But suppose I want to do something like this. If I want to write a program called grades.c, and this thing has to somehow manipulate grades for a course, I'm going to do something like int main, int argc, char star, argv. And now if I want to write a program that manages all the grades I get in a semester, well, I could do something like this. And for simplicity, we'll say grades are a number from 0 to 100. All right, so my grade for course 1 is going to be an int, course 1. My grade for course 2 is going to be an int course 3, int course 4. Now I need to put values in these. So I'm writing a program so that I, the sort of geek in my dorm room, can do things later like course 1, I can do something like this. Printf, like, hello, me. What did you get in course 1? Question mark. Close parenthesis. And now I'm going to do something like what? Course 1 gets, what would you propose? Yeah, so gets int, for instance, from the CS50 library. That immediately begs the question that how do I make that happen? Well, I need standard I/O for printf. I need the CS50 library for getInt. And then, OK, I got that one course. Now let me do a copy paste. So I'm just going to paste this 3 times. Incidentally, these little keyboard tricks I'm doing, if you again go to the course website, resources, there's little instruction sheets for Nano, for Vim, and also Emacs, which is another one. So I'm just going to, I know how to change things around. I'm just going to change this to a 4, a 3. OK, so this will work. right? This program works, and arguably it's pretty clean, it's pretty simple. It's hard to find a huge amount of fault with this, but I only take 4 courses this semester. Next semester, I'm going to take another 4. After that, another 4, 32 or more maybe in the end. So, OK, I can get a little creative here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines of code. So I'm going to get 12 so I get the white space. OK, so here's fall. There's spring. Sophomore year, sophomore spring, junior fall, junior spring, senior fall, senior spring. Good. Now my program's coming along. OK. At this point, this should be rubbing you the wrong way. Much like some of your larger Scratch scripts probably started to get out of hand after a while, especially if you were copying or duplicating scripts or nesting things a lot. So, even if one has not taken a course in computer science, hopefully the act of programming is not as tedious or as naive as just copying and pasting like I've been doing in Microsoft Word for years. So there's clearly an opportunity for a construct here called a loop, right? A for loop, a while loop. But there's kind of a problem, at least for those who don't have any programming background. Even if I have a loop, I kind of still need 32 of these things, right? So I need a lot of these. And thus far, we've not seen a way where you can create a new variable inside a loop, but create a new copy of it. We've declared the variable I inside of a loop, but we don't get a new copy of I for every iteration, right? Usually, we're incrementing the same copy of I. So we need a solution to this problem. I need a way of representing 32 ints, and I'd really like programming not to be as awful as having to define 32 separate integers, and then me, the human, remember what the name of all of those things are called. And in fact, there are. So one of the nice things about C and most languages is that they provide us with this thing called an array. And I used this language in week 0 when we talked about Scratch, because Scratch has things called lists, which is sort of the child-friendly name that they gave to the notion of a list or an array. These things are also called vectors in some contexts. Linked lists will be something related. They're all different in certain ways. So what we define today is actually distinct from what Scratch did and even from what some other languages do. But this is a little excerpt from a really nice tutorial online that we also link on the course's resources page about what an array is. So we've talked about memory already today. So it turns out that, and let me try to make use of this for 1 second. If, again, your computer's RAM is just a big rectangle, so from byte 0 on up to byte like 4 billion if you've got 4 gigabytes of RAM, well, what I'd really like, if this represents my RAM, if I want to have courses if I want to have 32 courses, I feel like I want to say something like int courses. But now I don't want to copy paste that. I want to say, give me not 1 int, but 32 ints all together. Well, the notation for this is to use square brackets, say the number of ints that you want, close square bracket, semicolon. What that has done is declared for me a variable called courses. That variable, though, is an array. An array of what? An array of integers. Now, what is an array? An array is just a contiguous block of memory that's been divvied up into smaller pieces, all of which structurally are the same. Put in real English, an array is just 32 ints back to back to back to back to back in memory. What that means is, whereas if I declare a single int called x, with code like that, that would carve out from my computer's RAM 32 bits and call it x. But if I instead do int courses 32, what I really get then is a whole bunch of ints here. And then, if they don't fit, this is just a picture now, obviously we're drawing, so they won't fit all in a row necessarily. So if I just count out 32 of these things, this is all going to be part of courses. But so this whole chunk of memory will have the name courses. Now, how do I access an individual course? Well, what I'm going to do is this. I'm going to go ahead and clean up the code I started writing a moment ago. So I'm going to delete all that junk. I'm going to get rid of this original approach. And I'm going to say something like int courses 32. Now I've got them. How do I now start plopping grades inside of each of these cells, each of these elements? Well, let's see. Course 1 is no more. Courses is a variable. How do you think I might get at the first element in an array? Yeah, so 0, we always start counting from 0. So courses bracket 0 equals getInt. And now down here, this becomes courses bracket, courses bracket 1 gets getInt. Let me do another copy paste just for now. Courses bracket 2 gets getInt. And do you now see where this can go? We already have the ability to implement loops in C. We have the ability to have counter variables in C, like I and J. So do you already see kind of in your mind how we can now rip out almost all of this code? Let me try getting rid of 100 lines at once. In fact, I don't really need any of these lines either. Now, this is not yet a loop, but couldn't I do something like for int I gets 0, I is less than 32, I plus plus. Give me little curly braces here. What did you get in course 1? I'll fix that in a moment. Let me close my curly braces here. There's a couple of problems. What's one I can fix easily? Yeah, so it's not courses bracket 0. Stop hard coding that. Courses bracket I. And then this 2 is a little weird. I can't hard code this. Now, obviously, that's not the solution there, to change the 1 to an I in that context. But what could I say? Course %d question mark, close quote, comma, I. So again, same building blocks, and already, voila. New idea. We just, deployed this really quick. We said you can have multiple variables, all of the same type, but give them one name and refer to them numerically in this way. Now we have the capability of expressing what in the beginning was a very simple problem. I want a way of inputting all of my grades. Well, let's actually look at a polished version of this. So in array1.c, I have this program here. And it's a little more interesting because I didn't want to just input my data. I wanted to then compute my average, which is slightly more compelling. So let's actually see the result of this first. So GCC array1.c. OK, getting defined. OK, I can fix that, right? -L CS50. Good. A.out. Enter. What were your quiz scores? So I got, let's say, 100 on the first one. Then I kind of screwed up. All right, so your average. Actually, you'll remember that comment now if you're the student that gets a 50 on the quiz, right? All right, so 50 is good. So 75 is my average. So right, you could do this on a calculator. But if you had 32 courses, it's kind of nice to let a computer do that. You don't want to have to do it all out by hand necessarily. So how does this work? Well, notice I'm incrementing some variable. So we already have the building blocks in there. I'm doing some mathematics. Feels like I'm maybe rounding to the nearest int, right? You would notice if we were just using a casting from floats to ints in this course instead of actually mathematically rounding grades at term's end. So let me go ahead back into this. This was array1.c. Well, let's see what I'm doing. Well, new feature. Turns out what I started to do on the fly there a moment ago was kind of bad practice. I hard-coded the number 32. And not only once, but twice. That tends to be bad practice. So that's what's known as a magic number. Magic in the sense that, like, where the heck did I define that value? All over the place. So another feature of C, and it's a little dark, I apologize here on this screen, is this ability to have another thing called the preprocessor directive. We've seen the sharp sign before. That thing sharp include is a preprocessor directive. There's another one that's useful. Sharp define allows you to define a constant. It's not a variable. It's just the symbolic representation of something, in this case a number, so that henceforth in my code I can use capital QUIZZES anywhere I want, and it's going to refer back to that same value. Now, just intuitively, what's an advantage of having used a constant like this instead of typing in 32? Yeah?
If your class has more exams, you can just go back and change that one.
Yeah. Exactly. If my class has more quizzes in the future and I need to store more grades, I just change it one place, recompile, and done. And in fact, even that's a bit of an annoying process. We'll also see ways where when I run the program, I could just tell my program how many quizzes we had that semester. We don't even have to hard code it. Now, the fact that I'm capitalizing it, this is a matter of style, convention. Almost any time you have a constant value, you should capitalize it entirely so that it stands out to you, the reader, and other readers, teaching fellows or other programmers, that in fact it is a constant value. So what's going on here? Well, let's see. I have a float called grades bracket quizzes. All right, so we've not quite seen this context yet in examples. Turns out if you want to have multiple variables, all of the same type, you don't need to put them each on their own line. You can just string them together with commas. So in that first line, I'm declaring an array called grades. I have how many elements in it? How many floats? So 2, as per the constant called quizzes. And then after that, I have another float altogether, a different chunk of memory called sum. And I also apparently had the foresight to declare a variable called average and one called I. And I start to use those here. All right, print, what were your quiz scores? All right, for I is 0, I is less than quizzes, I plus plus. All right, quiz number percent. All right, this is easy. I know what this is. And here's the line of code that we already did on the fly, albeit with getInt, grades bracket I gets getFloat. So realize 0 indexing is important. When the compiler gives you memory, you get 0, 1, 2. If you start counting at 1, what's going to happen is 1, 2, 3, 4, 5, 6, 7. That's bad, right? You want it to end at 6, so to speak. All right, so what do I do next with this value? All right, so now I have a sum. How do you compute a student's average? Well, you take all the grades, you sum them together, and you divide it by the total number of quizzes, right? Old school stuff. So sum is initialized to 0. For I is 0 on up to quizzes, so another for loop. All right, so this is easy, right? I'm just adding to sum inside of this loop the ith value of grades, which is just 2. But again, realize the dynamism of this program. Just by changing that constant, I could do this for a whole semester or a whole 4 years worth of college. So now here's an interesting trick. And I'll offer this just as a little teaser for now. To compute a student's average is really the result of taking the sum, dividing by the number of quizzes, but then there's this 0.5 trick. So for those of you who want to think this through, actually for problem set 1, this 0.5 trick, this is how you can implement the notion of mathematical rounding. And I'll leave that as a little thought exercise. But if you think through what might happen to your grades if you do and do not include this 0.5 and then proceed to cast to an int, casting has the effect of truncating everything after the decimal point. So there's actually a very clever magic that's induced by adding 0.5 before you throw that stuff away. So the person who wrote the round function in the math library, odds are they did something very similar to this. And then finally, what's the average? Well, I just print out the result. Well, just to show that you don't need to use that little trick, array2, which you have printouts of, is the exact same thing, but I decided to use the round function explicitly instead of rolling it myself. OK, so enough about math, though, because we've kind of dwelled on this for some time. Let's actually start manipulating things that are more genuinely useful, and those are strings, right? Because problem set 1, even though it's largely grounded in numbers and arithmetic, that's really just a design of necessity. It's kind of hard to do more sophisticated things when you've not yet even written one for loop or one while loop in C. So it's meant as a stepping stone. Problem set 2, though, is going to introduce you to another real-world domain of cryptography, the art of concealing information. Information is often expressed in English or some other textual language. And so that begs the question, how do I somehow manipulate actual characters, actual strings, actual paragraphs, or entire letters of text? So here's a simple example that's going to get us there. It turns out that what we called last time a string, we already know a string is synonymous with the slightly more confusing char star, the asterisk. So again, we'll tease apart what that means. But a string is a char star. For today's purposes, what a string really is it's an array. Not of ints, but an array of chars, array of 8-bit characters. So that kind of makes sense, right? If an array, or if a string is just a contiguous sequence of letters, you know, FOO or HELLO, it kind of makes sense that, you know what, the perfect data structure for strings, if we're not talking about ints anymore, but are instead alphabetical letters, why don't we call this something like S, the string S, so then I can put the letter H there, E, L, L, O, and so forth. Feels like it makes perfect sense to actually store a string in an array because I already get this built-in feature of storing things back to back to back to back and not all over the place in memory. So this program here is called string1.c. Notice that I'm using a new library up here, string.h, for reasons we'll see in a moment. Now, what am I doing? Well, I've removed the comments for today's training wheel removal purposes, but this line of code there simply gets a string from the user. Not an int, not a float per se, but a generic string. And in fact, it's going to store it. GetString is going to allocate a bunch of RAM like this. And whatever you type, it's going to put the first letter here, the next letter there, the next letter there, and so forth. And then it's going to hand you back that entire chunk of memory. So I do need to do one sanity check. And this, too, is a teaser of sorts today. It turns out that if the user is malicious or foolish or there's just some problem that you didn't anticipate, we need to sometimes have return values that are not legit values, like the actual string, a return value that's not the actual number you were expecting, but some kind of sentinel value. So a special value that you, the programmer, can check for. And if you get back that sentinel value instead of a legit value, you know something went wrong. You can check for it. And error checking was one of the topics for Monday. So it turns out, and you would only know this from reading the documentation or being told it in class, getString maybe can return a special value called NULL in all capital letters. So we'll use this throughout the semester. So today we're just scratching the surface. But this is just a special value, NULL, that when you check for it, if you get it back, it means the user did something like never typed anything, or just hit enter immediately, or just tried to generally mess with you, or did something you weren't expecting. So the very first thing I do in this program is I check. If S does not equal null, that's a good thing. Let's proceed to do something with it. I now have a for loop. For I gets 0. I is less than, oh, this is interesting. Take a guess what this briefly named function does. String length, strlen. So this is a common feature in C, right? Why say string length when you can say strlen? Well, how does that? That's a function. It exists in the string library, whose header file is called string.h. Now, even just as a little tangent, how would you, the human, implement string length? Well, I'd probably start looking at my chunk of memory and just start counting. How many legitimate values do I actually see? Now, it turns out there's going to be a special value that will store at the end of a string. \0 is literally the value 8 0 bits in a row. So it's a special value. It's not quote unquote 0, which is an ASCII character, but rather a special sentinel value. So strlen, as we'll see eventually in more detail, actually iterates over an array like that to get its length. So what does this do? Well, notice C is a char, because I declared it up here. S is a string, because I got it here from the user. And S bracket I gives me the ith character in the string, and then plops it in the variable called C. So what's the end result? Well, let me go ahead and run GCC on string1.c. OK, so undefined reference, again, -l CS50. OK, so a.out, enter. OK, it's not doing anything. Why? Right, because I didn't say printf. I really cut some corners here. So hello there, exclamation point, enter. OK, HELLO, comma, space, THERE, exclamation point, all on a separate line. Why did that happen? Well, this was string1.c. That's precisely what should have happened, because in this for loop, I printed %c, which is the new format code for just a character, \n, and so I got everything on a separate line. So in fact, had I done something maybe a little less weird and just compiled this and rerun this, now I have a sentence here, enter. Now I get it back. Now, granted, I forgot one new line altogether, but all this program demonstrates is that a string that you can fetch from the user by way of getString hands you effectively a chunk of memory that you can iterate over with this bracket notation, just like you could a whole bunch of grades from your coursework. Well, string2 has a slight variant on this. So in string2.c, I do something slightly more intelligent, which is good design. So this speaks to this axis of design. Notice this. What have I done differently here? If you can think back or on your printout, see the difference between that line and the previous version. A little louder, anyone? Yeah, so I have two initializations. So notice at the left, I have I gets 0, comma, n gets strlen s. Why did I move or add this declaration of n and assign it the return value of strlen in the initialization part of the loop instead of, I'll scroll back if you haven't the printout, instead of putting it right here in the condition, which was really nice and clean and sensible? Yeah, because this approach, elegant though it is, it's nice and compact, right? Looks like a really good piece of code, but remember that the condition is checked every iteration, which means the code inside this condition is executed every iteration, which means you're calling the function again and again and again for as many times as this thing iterates. Now, what does that mean? You're checking the length of this string by going 1, 2, 3, 4, 5, return 5. again and again. 1, 2, 3, 4, 5. Return 5. 1, 2, 3. I mean, this should feel stupid because is this string changing length in any way? Well, no. So there, too, is an opportunity for optimization, for a little bit more clever design. And so thus in string 2, do I actually call that function once? And I wanted to be a little elegant, so I put it in the for loop. I could have just done this and get strlen of s here. And then I didn't need to use this comma notation. So again, there's often multiple ways to implement a particular goal. But realize that was a fundamental improvement, because I'm not calling the function whose value is never going to change more times than is strictly necessary. So let's use this same feature to do something that's more useful. So it's a little weird looking code, but it uses all the same building blocks we've been using for days. So this program is set up as follows. Get a string from the user. OK, that's old hat now. Now what? Iterate over the string from I up to the length. OK, we just did that. So this code is the same. So the only new magic here are these 4 lines. Now what is this saying in English? If the ith character in s is greater than or equal to lowercase a, and the ith character in s is less than or equal to the value of the lowercase z, what do you think the next line of code is doing? It's just capitalizing it, right? How? Well, mathematically, and I won't dwell so much on the arithmetic here just because it's the same stuff as a week ago. But notice, how do you capitalize something? Well, let's just do the math quickly for one example. Little a is 97, right? I've promised this would be useful. So little a is 97, big A is 65. So no matter what I'm doing, I'm going to be subtracting, right? Because I got to take big numbers and make them smaller if I'm going to go to like 97 and above to 65 and above. So I have the value of s bracket I here. Then I do subtraction. Now, what do I subtract? Well, technically, I just need to subtract 65. But if I put 65 in here, again, kind of a bad thing. It's a magic number, like why 65? Well, why don't we just go ahead and do this? The difference that we want to subtract off is always going to be this, a minus a, little a minus big A. So let's just subtract things off a little more dynamically. And again, the astute can push back and say, why are you computing a minus a again and again and again? It turns out compilers can be smart, and if they realize you're doing some arithmetic that's never going to change, sometimes the compiler can optimize that for you. But for today, we offer it just for clarity. So if we go ahead and compile this, capitalize.c, damn again, -l CS50. But again, these errors should no longer be intimidating. Let's go ahead and run a.out on capitalize. Hello there, exclamation point. And good, it preserved my space. It preserved my exclamation point. So I actually did get this right. All right, so let's lay the stage now for where we're going with this. So 2 quick comments. One, by far, if you're feeling like you're not among those with books in hand or you just like learning stuff online, these are the 2 places to start, because it covers the stuff we've been looking at. But let's now pull back a layer that I've been waving my hand at for a week. You have, for any program you've been writing, used int main and then int argc, comma, char star argv. Well, char star is string. So that's the synonym for now. So it appears that main, all of this time, has been allowed to take in 2 inputs, an int and also a string. All right, so what does that actually mean? Well, it means that just like I can run gcc and then say foo.c, I can apparently pass inputs to so you got to say something sometimes. I can apparently pass inputs to programs like GCC by just writing those arguments on the command line. OK, so it's not quite an argument in the sense of a function, because this is a very different context, right? This is my so-called blinking prompt. But I can have clearly been doing things like -o, foo, and then down here I've been saying things like -l, CS50. So there's many different labels the world has slapped on these kinds of words. Switches, flags, command line arguments. We'll typically call them command line arguments. But you've used these before anytime you've typed commands. Even nano takes a command line argument. What is the command line argument that nano is supposed to take? The name of the file, right? So we have this ability clearly in Linux, in Mac OS, and in other contexts too. So how do we get at that information? Well, in argv1, we see a very simple example. Notice here that in this function, in this main function, I print a new line. And then I do this. For I is 0 on up to argc. So take a guess. What does argc maybe represent? Argument Count, argc. It's a convention. I could have called it x and y, but the world kind of standardized on these two nicknames. Argc is argument count. So if I want to iterate over all of the words that the user typed at the command prompt, I can iterate from 0 up to argc. Well, what is inside of argv? Argv apparently all this time has been an array because of the bracketed notation. What is inside that array? Well, not just characters. It turns out that inside of an array can you also put other arrays. You can put strings themselves. So this is, if you're really thinking this through, this is like a two-dimensional array. But we'll get there. So argv in this case is an array not of chars, but of char stars, aka strings. So what does that mean? Well, let's just compile this and try to infer what's going on. GCC argv1.c. OK, good stuff happened. So a.out, enter. OK, not such good stuff. All right, so how about foo bar baz? OK, so apparently my program has the capacity to just spit out anything I type. Let me just get a little familiar, like a.out foo.c. So think of this as running nano. So it looks like also inside of argv is not just the words after the program you ran, but what else? The program itself, which is useful. So in short, argv contains all of the words a user has typed at the command prompt, including the command or the program name itself from 0 on up. So all this program does, notice, is this. It iterates from 0 to argc. OK, pretty simple. It's just integer incrementation. And then what am I printing? Well, %s is a new format code 2 here today. So this means put a string here. Not a decimal, not a float. Put a string here. What string? Give me the ith word inside of argv, the ith argument inside of argv. We can get more creative still. If I open up argv2.c, this looks a little fancier. And we won't dwell so much on the syntax because, again, we have seen things like this. Here's a for loop iterating over I. Here's another for loop iterating over j. But notice what this program does if I just reveal the magic here, argv2.c. So ra.out. Oh, interesting. So I'm just getting a little aesthetically interesting. Foo bar baz. So here, apparently I'm iterating not only over each of the words the user typed, but also over each of the characters within. So I hinted a moment ago, and we'll see this in more detail over time, but an argv is really just a two-dimensional array. An array of strings, but strings are arrays of chars, so that's an array of chars. So how am I doing this? Well, I iterate over the arguments from 0 to argc, and then, oh, here's something familiar. Again, I've just been taking baby steps over the code today. Here's j is 0, n is initialized to the string length of the ith argument. OK, iterate from j to that length. And oh, this is interesting. If argv is, in fact, a two-dimensional array, an array of strings, aka an array of arrays of chars, turns out you can put brackets back to and back if you know it's this sort of two-dimensional array. So argv bracket I right here, this gives me the ith word. What does argv bracket I bracket j give me? The jth character in the ith word. So it's actually fairly straightforward. Again, some new syntax, but fairly basic building blocks. So here's the canonical list for now of functions you can use that will be used not so much for problem set 1. For the most part, you've had already the basic building blocks for problem set 1 as of last weekend, this Monday. But for now, before we start looking at the code, here's a quick reminder of what functions are in CS50's library. The last one of which is this latest one, getString, returns a string. But remember, a string can be manipulated with this bracket notation, as we've been doing. Now, for the astute too, at the top I disclaim memory leaks. So CS50's library is buggy intentionally. We allow ourselves to indulge in what's called a memory leak, whereby we are actually allocating a whole bunch of RAM for you, and we never ask you to give it back. So realize that we'll have actually an interesting opportunity to discuss that. But where are we going with this, and why introduce this at all? Well, clearly we got to arrays today, and that's kind of a juicy new feature. But we can do this in a more interesting context, such as cryptography. So we introduced Monday with Ralphie. We had that expression, be sure to drink your Ovaltine, which is repeated here using rot13, rotate 13. Just rotated all the letters 13 places, and that's the nonsense you get out. But it was a specific instance of something we called a Caesar cipher. A cipher being an algorithm or program that scrambles information. So this is very similar in spirit to some very real-world things. This is the German Enigma machine. You can read up on this on Wikipedia. It's covered in many movies and books, certainly over the years. We've seen real-world incarnations of cryptography. This is essentially a really fancy typewriter with really special, really secret gears and levers that when you type out a message, what gets spit out is something that looks more in spirit like this. But the Germans were smarter than just, rotating all letters in the German alphabet by 13 places. That's why the Americans and Allies were so intent on stealing boxes like this so that they could figure out what those messages were. But what we'll look at this coming week is this notion of cryptography. And this is sort of a fancy depiction that I'll actually wave my hand at just so that we can look at this guy here, Caesar, supposedly. Naive though this algorithm might seem all these years later, used simple cryptography to send messages to and from his generals in the field. And they did so by way of writing them down on a piece of paper and then rotating all of the letters, as the story goes, by some number of places, so that A became D and B became E and so forth. So he and his generals had a secret that they whispered together before they went off out to battle and such. And he said, 13. Or something like that. Right now, it's a fairly simple cipher. Even I have sort of trouble imagining that there weren't still, even back then before computers, really smart people who maybe by trial and error might have figured out how these messages were encrypted. But for us, it offers a really interesting opportunity because just as I've written, just as this figure presents these letters from left to right in a grid, it suggests that just by using a little bit of arithmetic, can we rotate letters. And in the event, if we go too far off, if we try adding 13 to the letter Z, we don't want to fall off into no man's land. We want to wrap around back to the letter A. And what simple building block have we seen whereby we can wrap around? Yeah, so the modulo operator. So that's where we're going. Now, all this time, throughout today's lecture, has Homer Simpson been busy at work with his little internet company. I thought we would conclude with this 20-second clip of how his internet business turned out.
Well, they have the internet on computers now.
Oh, no, Bill Gates is here.
Bill Gates? Billionaire computer nerd Bill Gates? Oh my God. Get out of sight, Marge. I don't want this to look like a 2-bit operation.
Mr. Simpson?
You don't look so rich.
Don't let the haircut fool you. I'm exceedingly wealthy.
Get a load of the ball job, Marge.
Your internet ad was brought to my attention, but I can't figure out what, if anything, CompuGlobal HyperMegaNet does. So rather than risk competing with you, I've decided simply to buy you out.
This is it, Marge. I poured my heart and soul into this business, and now it's finally paying off. We're rich, richer than astronauts.
Oh, McGuire, you'll queer the deal.
Oh, I reluctantly accept your proposal.
Well, everyone always does. Buy 'em out, boys.
Hey, what the hell's going on?
Oh, I didn't get rich by writing a lot of checks.
Have a good weekend. We'll see you Monday.